just listened to was The Police, 1983, and that was Sting with Every Breath You Take or I Take. Every Breath You Take, and that was Sting with The Police back in 1983. Neat music. I can just sit there and listen to that for at least another hour. However, we'll do something equally as exciting. Yeah, we're going to do mathematics again, so I'm pleased with that. Now, I've heard some critiques, some grumbling, no less, that what we did last night was a little more frustrating than usual, a little bit harder than usual maybe, and that may be. We did some fractions. We had to find common denominators, and yes, LCMs. So yes, a little bit more difficult. That's what will happen, and it will continue that way. We're going to review much of this process this morning with fractions because we're going into the 11th review, and the 11th review is finding LCDs using primes. So up to this point, you didn't have to use primes, but you could. Before I do that, just so you are not confused and thinking, okay, why are certain things left on the board? So at this point, Ernie, if you could just take the content that we have up here. I wanted to explain a little bit what I left here because otherwise there are a lot of questions, I suspect. Okay, you want to make that cut to there, Ernie? This is what we were doing at 7 o'clock this morning with the stat class. And we're going to do what is called a graph in this class. We are going to plot points. And we are going to do something very similar to what you see here later on in one of the units in the orange book. But I wanted to share with you what is involved here, and it relates to mathematics. For what I'm asking you to do in this problem, you could do with what we finish in this course. Now, this problem comes out of some data that was provided for 2006 by the CIA. It's online. It's called the World Fact Book. And what they do in that is look at over 200 countries in the world, and they collect information. So this particular information involved birth rates and life expectancies. Now, the birth rates are for data about number of babies born in a country for every 1,000 people. So here was the data set. These were 5 countries, the first 5 countries listed. And by the way, that first country is Afghanistan, with a birth rate of 46 children per 100,000 population. The last one is Andorra. Now, you know where Afghanistan is, I think. You've heard enough about it. Andorra is where France and Spain meet. There's a mountain region called the Pyrenees, and Andorra is between those. So there are nearly 9 children born per 1,000 in Andorra, but in Afghanistan 5 times that much. But look at the life expectancies. These are in years. Now, there was a glitch in that first number. I reversed 2 digits and shouldn't have. 43, roughly, is how old a woman can expect to live in Afghanistan. In Andorra, nearly 87 years. Huge difference. Okay? Now, as we look at what's on the board, all I did was take that information and each pair I graphed on the board, and you get what appears to be a kind of line that fits the data. So the line steps up here and comes down, and all it's saying is the higher the birth rate, the lower the life expectancy. By the way, the lowest life expectancies in the world right now are under 40. They're in the 30s. Okay? The highest is that 86. Okay, but think if your life expectancy was 30. And of course, the argument here is what's causing all this? And so part of the explanation for life expectancy has a lot to do with how many children you have. So if you go back a couple generations and you look at your family history, my guess is you'll find it was quite often that there would be a family with 9 to 15 children. Now, it's much more common to have families with what? 3 or 4, maybe 5, but oftentimes 1 or 2. Now, if you're having children, 12, 15 of them, in a 30-year range, that's about every 2 years a child, what happens physically? Wear down, potentially. And so one argument is just having more children may make it such that you have a shorter life. Now, one of my students in the last hour said her grandmother lived to 100 and, was it a 104? I think it was a 104 or 106. Must be 104, and had 16 children. So certainly not every case. My grandmother, I think, had 11 and died in her 50s. So quite a contrast. But generally speaking, the argument is the more children, the shorter the life expectancy. So this came out of some work done in 1994 in Cairo, which was called the Cairo Conference on Population Development Problems. And I think you're familiar with those problems. They affect us. They affect the world. Some of those problems right now that we're talking about, global warming. There's a lot of argument, but we seem to be having warmer ocean temperatures. Katrina, a result of that. Hurricanes. We talk about the ozone layer and the fact that the ocean levels are going to rise. So places in Oakland, San Francisco, Foster City, if the oceans rise, go underwater. If you're thinking in terms of places globally, Venice in Italy, just barely above water, and it floods already at times, that would, again, be a problem. So these are problems in population development, and just for your information, large numbers that we talk about, there are roughly 6 billion people on the planet right now. And they're talking about this going up to 10 billion by 2020. Okay, that's a pretty good increase, double the population nearly. So that's what we were talking about, and we spend an entire semester looking at that, and the prerequisite for that course is an algebra course. But we could do this same problem in here at the end of this semester, plotting points, trying to estimate the line that goes through the points, and then we try to give an equation of the line, and this, by the way, happens to be the equation down here that we estimated. So that's going to stay in the board. I need that for tomorrow's discussion with the stat class. I didn't want to have to redo that, and that's what we'll be doing in there. Our work in here is lesson 11, and that is continuing where we were yesterday. Just a reminder, at the end of the week, I'm very much considering the test on the counting unit. So what are the things you need to be doing? This adds a little more onto your plate, but I'd like you to get the unit done in the orange book, the counting unit, and I am thinking in terms of about a 40 to 50 minute test. On Thursday, you would turn in your book while you're taking the test. I go through the orange book giving you credit for that if you've got all your work done. So with a little bit of time we have left today, I'll spend some time on counting, again, just reviewing a few things. We'll do the same thing tomorrow. And then with the idea on Thursday that you're ready to take that test. Yes, question?
Will be primarily on the orange book?
Yeah, the test that we would have on Thursday, orange book only.
Okay.
That would just be on the counting unit. Okay? Now, how do we find common denominators using primes? That's the argument. Okay, we're going to use the stair-step method of division. Write the denominator as a product of primes. So I need to come up with a new problem. We did an interesting one the other day. We did 48 and 56, right? So we need something a little more interesting than that. So we had a 48 and a 56. So Ernie, let me come up to the board now and see what we can do. I'm going to start with the 13, and I'm going to subtract the 5 down here. I need a denominator that's a little more interesting than what we've been doing. So we had a 56 and a 48. So why don't I take, I'm thinking of some numbers I can use here, and I would have 72 up here for a denominator. And in the one in the bottom, just for the sake of argument, a 75. For this numerator, I want something that won't reduce with it, so why don't I make that a 5? And down here, again, something that won't reduce with it, and why don't I make that a 14? Okay? Now I need to change those denominators to a common denominator. Does anybody just eyeball it and see it immediately? Because I don't have it in my head yet. Nobody has it yet. Okay. So I'm going to change these to an LCD. That's what I need to get. Now, what am I going to do? First step. Anybody? Well, before I divide, I might want to list them. Okay? Now, how far do you have to go? Typically, not much more than down to 13. We'll just slide over Ernie again, pretty much here. And you're on camera 2. Okay. So at some point, eventually, I'll have you going back to 1 here, 2 here, and so on. So you're okay with 2 being on here. I'm going to start with the 72, and I start dividing by what? The lowest prime in my list. So I have a 2 here. Now these divisions should be just coming off the tip of your tongue about as fast as you can write them. 2 into 7 goes 3, remainder is 1, so that gives you a 3/6. I've been saying numbers in different bases so much I didn't even say 36, just said 3/6. Then do 2 again until you can what?
18.
Not do the 2. Because each time I'm getting an even, I can do 2 again. But this time I get a 9, which is not even, so I'm done with the 2's, and then I come down to what?
3.
The next prime, which is 3.
1.
And I go 3 again, and I get a 1. So what am I going to do down here?
2 to the 3rd.
I have 3 2's, so 2 to the 3rd, and 3 to the 2nd. I heard that, the 3 to the 2nd. And this is my 72. Then what do I do? Same thing with the 75. Agreed. So I'm going to take a 75 here. Same argument. Can I do it by 2 this time?
No.
No, because it's ending in a 5. Now you might say, well, I'm going to go to 5 right away. Don't. Stay in order. Start with the 3. So I get a 2. Remainder. 2 times 3 is 6. 6 from 7 is 1. And yes, I'm going to put a 5 up here. I agree. And there's no remainder. So I end up with 25. You know 3 won't go into 25, but how do you check? Add the 2 digits. 2 and 5 is 7. 3 will not go evenly into 7. So I'm done with the 3's. 5 is next. I get a 5 again. And so I have 75 is 3 to the 1st, 5 to the 2nd. Are we in agreement? Now I need a what? LCD. So I'm going to build it now. So I start down here with LCD, and I'm going to have what? What primes did I use in my division? I used 2's, 3's, and 5. That's it, right? Now the fact that I use them more than once doesn't matter. I just used 2's, 3's, and 5. So I write down what I used. Now what exponent do I want? Give me the argument. The largest exponent, right? So for example, on 3 I had 3 to the 2nd, 3 to the 1st. The largest was a 2. Now you didn't have any problem with the 2 to the 3rd because there wasn't another factor with 2. And there was no problem with 5 to the 2nd because it's the only one you had. So it's 2 to the 3rd, 3 to the 2nd, 5 to the 2nd. What is that number? Okay. Well, 2 to the third is what? I've heard about 4 different numbers. Let's check. 2 to the third means I have 3 2's multiplied together. So that's 2 times 2 is 4, times 2 is 8. Agreed? So this is an 8. What's 3 squared? 9. So there's my 72. So my LCD is that 72 times 25. Big number. We're in trouble. Okay, 5 times 2 is 10. Carry the 1. 3, 6. And then a 4 and a 14 and a 0, a 10, an 8, and a 1. Do we agree? Yeah. 1,800. Okay, coming back down here, here's my LCD. So my 5 squared is 25. The 3 squared was the 9, and the 2 to the third was 8. So I have 8 times 9, that's 72, times 25. So I took 25 times 72, and I'm getting a very big LCD. I didn't realize how bad that would be. But can you imagine counting by 72s until you get to 1,800? And counting by 75 until you get to 1,800? I can't. Two of you nailing me on this. Oh, there's more? Don't fret. There are more ready to nail you. Okay. Let's come back now, Ernie, over here. Now we have an 1,800 here. It was a very good year, 1,800. I read about it. I wasn't there. Okay, now I want to change each of these fractions to something over 1,800. I don't want to divide 75 into 1,800. That's terrible. So what am I going to do? Sesame Street time. Okay, backing up, panning over here. I'm going to go to a comparison. Okay, let's look at this. Here's 2 to the third, 3 to the second. That's the denominator I had. And what do I want it to look like? This. So what is the only thing I'm missing? 5 squared. Compare. How do they look different? If this had 5 squared, it looked just like that. But it didn't. So if I multiply this by 5 squared, I've got it. Okay, I have absolutely no way of reading your expressions right now. They are just so poker-faced that you could bet everything and nobody know if you're bluffing or not. Okay, so we're going to multiply 25 times that 72, so up here, and this is pretty nice. Now, this was not planned ahead, but you know what 5 quarters give you. That's a place value in base 5. So you know immediately that's 125. So I lucked out. I got a very nice numerator out of that. Any questions on that step? What do we call this when I multiply the denominator and numerator by the same thing? I'm trying to get a common multiple in the denominators, but I don't call that process. BPF. Basic principle of fractions. Whole lesson on that. Okay, backing up. Okay, let's do a comparison again. Here's what I had for this denominator. Here's what I'd like to look at. The 5 squared's okay, right? But I only have 1 3 here, and I have how many here? 2, so I need a 3. So if I multiply this by a 3, they'll match. And what else? 2 to the third. So I need to multiply this by a 3 and a 2 to the third. So if I multiply this times what I have, it'll look just like this. Do you see that? What is 3 times 2 to the third? 2 to the third, we said, is 8. And 3 times 8? 24. So this list wouldn't have been all that long, just 24 numbers in the list, 25 numbers in this list. That might have been fun, if you have a warped sense of fun. Now the question, what's 24 times 14? Let's see, where can I write that? Let's do that over here, Ernie. So let's slide over. So I need 24 times, we said, 14. Okay, the 56 is the first one, right? Then an X and a 28. And so I'm at a 6, a 13, and a 336. Really? We saw that yesterday. I heard it. We did?
So we're going to have to
Where did we see it yesterday? That was the LCD for what?
11 for 5 and 11 for 48.
Was the 48 for a denominator and a 56 for a denominator? So that's a friendly number. You've been there. You've seen that. Now, I'm supposed to subtract. I'm in trouble, right? Because this is bigger than that numerator. So I have to borrow. Okay, so 13 minus 1? 12. Where do I put the 1 I borrowed? This is critical. Where you put this 1 is very critical. Where are you going to put it? That was a subtle hint. Create the space. There it is. That's where that 1 goes. You don't put the 1 up to what? Right next to the 1, 2, 5, because that is the error you want to avoid. Now, what's my shortcut? Just add these two numbers. 1925 minus 336 over 1800. Was that the best thing to do right away? What would be your argument? Very good. The response was no, because I should, before I get all caught up in this, subtract the 5 from the 12 and get that done right out of the gate. Because if I don't, after all this mess working with the fractions, I'm likely to forget it. And that costs you some points on a problem. It also gives you a wrong answer. Okay, let's get the next step. Let's see what we get. We know it's 7 and something.
1581.
I'm hearing a 1581 over an 1800. Now that is your basic rotten fraction. They don't get much worse than that, I think. So the question, can I reduce it? Can I reduce it? Now that seems maybe beyond anything you want to consider. But what are the only numbers I have to worry about? Ernie, back to the other camera. The only numbers I have to worry about are the ones I used for the LCD. 2s, 3s, and 5. A 2, 3, and 5. That is very nice because I know those rules for a 2, 3, and 5. Let's go back. What's my rule for 2? Even number at the end, correct? I have 1581. It's not even. 2's out. Only two more numbers to check. A 3 and a 5. While we're at it, is a 5 an easy one to check? Yeah, it has to end in what to be? 0 or 5. It didn't. So 5's out. The only number to worry about is
3.
a 3. Okay, 1 and 5 is 6. 6 and 8 is 14. 14 and 1 is 15. 3 will divide 15. 3 will divide that number. 3 into 1800 is 600. I divided by 3. Okay. What tune?
Crud.
The title of a new song, Crud. Okay. By which group? I'll leave that alone, I think. Okay.
Yeah,
3 into 15, 81. What do we get? 3 into 15 is 5. No remainder. 3 into 8, 2, with a remainder of 2. So that would be 527. Agreed? Now, I don't know why my lines went in opposite directions. Interesting. There has to be some deep philosophical reasoning going on there that I don't understand. That's what it looks like. Okay. Now, will 3 go into 527? Check. What do you get for the sum of the digits? 5 and 2 is 7. 7 and 7 is 14. 3 will not go into 14 evenly. You're done. That's it. So your answer, 7 and 527/600. Basic, rotten problem. But it was fun. It depends on what you consider fun is. I had fun. You may not have fun. We'll see.
I had fun watching you.
Okay, that's okay. Well, I needed to take, I'm being critiqued again, that this took 20 minutes to do, and we won't have that long. Well, I won't give you a problem that messy. But if you can handle this, it's a little bit like a safe driving school. I want you to handle freeway speed, so I take you out at the Autobahn and have you do 180. Oh, what do you mean, all right? And then put you on a freeway here, and you go 35 because of gridlock. Always find that interesting. 70-mile-an-hour speed limit, and it's so packed you can't even do 5. Okay. Any questions? We got it? More or less? We'll just leave that. Are you on camera 1 now? Good. Then what I'm going to do, Ernie, is head over to open space. I feel like I'm going west, young man. So at this point, there's 2 problems with that. Not young man, and 2, I'm not going west. I'm actually going east as I walk towards there. But anyway, are you ready for me to head that way? We'll leave this one on the screen so you can see it. Let's take a momentary break. I'm going to do counting for a moment. Let's see if we can have some fun with that. Counting. Here was a request from the last hour. Doing things by request. Feel like I'm a DJ. Okay, we're going to do a request. Here was the request. 140 base 10 as base 5. What will you have? Where do you start? And this is sort of out of the blue, I realize, but nonetheless. See, we could do Out of the Blue as a song, too. Where do you start? Somebody. When you say lines, do you mean something like this?
Yeah.
Okay. So we're going to talk about place value. Now, what's the base I'm interested in? I gave it to you in base 10, but I want it as base 5. So I can either write 5 to the 0, or I can write a 1, your choice. I sort of like the 5 to the 0. And then your base, which is 5, those are nickels. Then that technically is 5 to the first. So stair steps again, since you talked about stair steps before. So that's a quarter, and then we get a Debbie, which she told me should be called a DC. So that's 5 to the third. Remember, that was the coin that was 125 in its value. So I want to write 140 as a base 5 number. Do I have, can I have a 125?
Yes.
Okay, I put that up here. So I could do a division problem and take 125 into 140, and it goes once with a remainder of 15, correct? So I can't have any quarters. Now the next place value is a 5, so I can take the 5 into the 15. It goes 3 times with no remainder, so my answer is 1030. We got it? That went okay? more or less. Now let me take a slight twist on that, just a little bit. Let's say I give you this problem, that I give you a 3, 0, 2, 0, 3, base 5. That's my number. What do you do to write it in base 10? So this time we're going backwards. Write as base 10. So what are you going to do this time? See if we get any. If you wanted to give somebody a big hint, what would it be? 2-word phrase. 2-word phrase. Hint. Anybody? Okay, so much for hints. I will write out the hint. Expanded notation. Good. We got it finally. Giving you a few more letters. What is that game they play where you choose letters and you get to try to guess the word?
Wheel of Fortune.
Is it Wheel of Fortune? You get letters, you get an A and an E, and okay, so we just did Wheel of Fortune with base 5. Okay, what are my place values up here? So let's write it out. 3, 0, 2, 0, 3. Now I gave you those place values just a moment ago. They are 1. I'm going to do it now without the base. So it's 1 and a 5, but with no exponent. Then 25. Then after the 25, we said 125, and then I'm supposed to do what? Multiply 5 times that, and you are indeed going to get 625. And you're just glad I stopped at that point. So now, over in the side, I'm going to say 3 625s. I'm going to say 0 times 125. That's nice. I get to do that one. Dealer's choice. And then I have 2 groups of what? 25, which gives you 2 25s. What do you get? Right, 2 quarters. Agreed? And then I have what? 0 times 125, and that's still a 0. And then I have what? Hold it, Curl, you just screwed up. I went backwards and shouldn't have. I already did the 0 up there. So I should be down to the 5s. My apologies. I'm down to 0 5s. That was really a bad D-A-E. Okay, now 3 times 1. Now up here I need to finish this one off. What is 3 times 625? Yes, good. 1875 I heard. And just hold there for a moment. Okay, now all we have to do is add, so I agree. This first column is an 8. The next is a 12, then a 9, no carry. So 1,928 base 10 is the same as, a.k.a., also known as, 30203. So this year, 1928, would have been written this way. Now, most cultures don't have the year this big with the digits. The Chinese, the Babylonian cultures go back the 3,000, 4,000 year period. But for most cultures, that's pushing. Any question there?
Can you also do it 3 times 10 to the 4th plus?
Question, could I just change this base to 10 here and say I have 3 times 10 to the 4th and so on? No, because you have to use expanded notation because this 3 did not mean 10 to the 4th. Now, if I told you that it was base 10, that would be a different story. But starting with base 5, you don't have that choice. Any other question there? What is the place value of the 2? Just looking at that problem.
1.5 and base 5.
Okay, I'm in base 5, the place value of the 2, and it is just 25. Right? Because it's right here. So I'm looking at this. And so the place value below that is the place value of the digit. So the place value of the 2 is 25. What digits do I use to write a number in base 5?
0 through 4.
0 through 4. There are 5 digits, and I always start with 0, and then it helps if you go to 1, then 2, then 3, then 4. Those are the digits I use. Is that seeming a little more comfortable now? Let's try what we did yesterday, a multiplication table. This is just for fun. And it would help if I could get a straight edge there. But let's try again. Okay, and coming across, an X up here. And I'm going to put 0, 1, 2, 3, 4 coming down here. 0, 1, 2, 3, 4 coming across here. What is my base? Base 5. So will you tell me, if I'm in base 5, what 4 times 4 is? No. 4 times 4. No. I'm hearing some numbers, and I'm just so far saying, no. What?
2, 1.
No.
4.
4 times 4 in base 5. There we go. I heard it. I did hear the number I was waiting for. Now, if somebody said this and I didn't hear it, I profoundly apologize to you, because you would have been right. 3 times 5 is 15 plus 1. There's your 16. Okay, let's take, we're doing perfect squares. So 3 1's a perfect square, base 5. 4, let's see, we want 3 times 3 base 5.
1, 4.
Do we agree? Head bob time, if you agree. Just go up and down. The answer given was 1, 4. Do we agree? 1, 4. Head bob? Okay. So one group of 4, and one group of 5, sorry, and 4 left over is a 9. Okay. 2 times 2.
4.
It's 4, just like it was before. Perfect squares. 1 times 1 is still 1. 0 times 0 is 0. So those are my perfect squares. 1, 0, 1, 4, 1, 4, 3, 1. Let's just do one more for the heck of it. 4 times 3. So I'm wanting the number right here. 4 times 3.
2, 2.
I'm hearing a 2, 2. Give me an argument.
5, 10, 5, 2.
Okay, 4 times 3 is a 12 normally, and that's 2 5s and a 2 left over. So we have a 2, 2. Is that something you wear? Okay, a ballerina dress is 4 times 3 base 5. Mess up your thinking forever. Okay, but that's a neat exercise to go through, to try to check yourself in other bases. I sort of like that. Any question there? Okay, let's digress. I'm going to bounce out of this now back to primes. Right, I think I'll probably write it up here, Ernie, so I don't confuse things. Right. I'm going to fill in a space as a product of primes. So I need to have a number in my head to do this. So I want to write some number as a product of primes. Does anybody have a number you want to give me? 1508. See, I don't take responsibility for this now. I'm guilt-free. But what do I still start with? The 2, the 3, the 5, the 7, the 11, the 13, the 17. I don't know if anybody heard the comment watching this at 3 o'clock in the afternoon, but the comment was, you're killing us with the 1508. Okay, so we start with the 1508 here. Is it divisible by my first prime? It's even, so it will be. So I'm going to take 2 into there. I get 7 with a remainder of 1. 2 into 10 will go 5, no remainder, and 2 into 8. Oh, I like that 4 because it means what? A 2 will go again. Life's getting a lot nicer. 2 into 7. 2 into 7. 2 times 3 would be your 6. Remainder. Okay, we're pulling numbers just wacko right now. A 1 here. And 2 into 15 is 7. Remainder. 1. And I get a 7. Okay, life suddenly went not so good. Why? 2's done because it ends in an odd number, a 7. Will 3 work? We get 17 when I add. 3 won't go into 17 evenly. 3 won't work. Will 5 work? No. So we've managed to take care of 2, 3s, and 5s. Okay, before I get running away with this too far, how far do I have to check? I mean, I could divide by 7 and divide by 11 and divide by 13. When do I know to stop? What do I have to check? Well, 15 squared is 225, and that's still smaller. 25 squared is what? 625. Remember the shortcut? The answer is no. Okay, 2 times the next number, which is 2 times 3, which is 6, and put a 25 after. That's your shortcut. Now, why was I worried about that? Well, that's bigger than what? This. Now, what are my primes under 25? I only have a 19 and a 23 to check. Now, 23 may be bigger than I need, and it is because what's 20 squared?
40.
Close. Good, wrong answer. 400. And is that bigger than 377? Yes, so I don't have to worry about 23. And 19 turns out to be 19 squared is 20 minus 1 squared, so that's 400 minus 40. That's 361, and that is smaller than this, so I may have to check up to 19. Okay, so we try each one. Maybe 377 is what? Prime. But I only have to check 7, 11, 13, 17, and 19. Okay, will 7 go into 377? 7 into 37 is 5, 2 left over, and 2 will not go into 20, or 7 will not go into 27 evenly, so I'm done there. So 7s are fastest. What about 11 into 3, 7, 7? Well, that's 3 with 4 left over. Won't work. 11's done. Okay, so then we go to what? 13 into 3, 7, 7. Okay, 13 into 3, 7. Let's try pulling that in just a little bit more, Ernie, because it gets a little bit too hard to read. And we'll just focus here. Zoom in a little bit more. Thank you. 13 into 37. Twice. That's 26. That's a 117. I'm waiting. I am waiting.
Yeah, 9 times 9.
Okay, that's a 9, right? 9 times 3 is 27. 2 carried. That's 117. That worked, right? Now that's not good because I screwed something up if that's the case. Because why would I say that's bad? Because if I got, oh, hold it, there's the 9. Okay, I was thinking I only had 9. It's 29. I was going to say if I had a 9, I could divide by 3, and I knew I couldn't do that. That meant I made a DAE. Okay, so we have a 29. So the answer here, this is a 13, and this is a 29. And what do we know about 29? It's prime. So what do we have up here? We have, fortunately, the end.
2 to the second.
So we have 2 to the second,
13 to the first.
13 to the first, 29 to the first. So 1508 was a very good year of 2 to the second, 13 to the first, 29 to the first. It worked. That was fun. Okay, we're back to Sting. You have review test 11 due tomorrow. So we are going to, it's not due yet. You can wait until tomorrow. And so we will close with the police. Did you choose a different title for the police? King of Pain. Boy, you really nail them.